Thanks, Morgan, and thanks for listening. Okay, so I'm thinking about the situation is that there's a lot of species in the world, and we actually know relatively little about most of them. There's about 300,000 flowering plant species in the world, and there's about 900 species of eucalypt trees in Australia. We know a lot about a few of them, very little about others. Now, I want you to imagine that you're standing in a forested landscape and you're looking for a particular tree species because you're an ecologist or because you're a manager, and conserving it, knowing where it occurs, matters. You know that it grows to 50 metres tall and that has moderately thick and dense leaves, and it has small seeds. Which way in this topographically complex, climatically rich landscape should you head? There's soil variation, aspect variation. Where should you go? And that's the problem that I'm interested in. So we could use trait SDMs for this. So trait environment models, or I'll call them trait SDMs. This work stems from Laura Pollock's PhD, and there's Will Morris on that listed paper as well. And this was emerged from working in the Grampians in Garryward, which is in Western Victoria. There's about 20 species of trees that occur in a 75 by 30 kilometre area, and they occupy different habitats in that landscape. And those habitats are correlated with the traits that they have. And we can build statistical models, these are just generalized linear mixed models, of the form like this in words, where the occupancy of the ith species at the jth site is a function of its prevalence, and the environment and the response of that ith species. And we can decompose the response of the ith species to the jth environment to it being some function of traits that that species possesses via some modulating coefficient. And this can be extended to multiple environmental gradients and multiple traits. And this sort of modelling framework has been followed by a whole bunch of people in different contexts. So Otto Veskainen's work, Francis Huey's work, David Wharton's work, Kaya Tabrak's work, okay? And I'm interested in, we got useful understanding of species distributions in this region, but can we generalise? So here is a bit of a map. This is where you're being streamed from in Sydney. That's where UTI is sitting at the moment. And I'm down here in Melbourne. This is about 900 kilometres from here to here. Here's our reference region, about 400 kilometres away. Can we train our trait SDMs in here and then transfer them to 18 target regions over here, at which there are a whole bunch of other species? So these graphs just show the distance in kilometres away from our reference region, showing that the nearest of them is more than 400 kilometres and nearly up to 1,000 kilometres away. And the environmental dissimilarity of these target regions from the reference region, and the Jacquard dissimilarity. So up here we have regions that share absolutely no species in common with our reference region. And down here we have regions that share less than 20% of species. So we are transferring to new regions and new species sets entirely. So that's what we want our trait SDMs to do. So how good are they? Oops, I need to tell you a little bit about the models, not too much. I'm just going to tell you about these partial dependence plots. So here we have for 4 environmental covariates and 3 plant traits. So in this one here, for specific leaf area and topographic wetness, this positive relationship tells us that species with high SLA, that's thin and flimsy leaves, increase in probability of occurrence towards areas that are topographically wet. They accumulate water from the surrounding landscape. Species with low SLA, their thick and dense leaves, have a negative response to topographic wetness. That is, they increase in probability of occurrence as you go to areas of the landscape that shed water, okay? Now, these models are not perfect. They're not very good. This is the amount of variation that occurs between species in each of these environmental responses. And this is the explained variation in the paler bars. So they're not great, but my point is rather, can we transfer them? I think that's not enough an evaluation. we can make predictions to target species. So here for combinations of low and high SLA in the columns and low and high seed mass in the rows for responses to topographic wetness and to moisture in the lowest quarter, which is going from hot, warm, dry places to cool, wet places. So for these different combinations, you can see that this one increases towards wetter areas and those but that are warmer and drier. And this one species combination increases to areas that are shedding water and that are warm and dry. Okay, so we can make segregated predictions. Okay, so how good are they? So we've got to get to, here's a schematic about how we're doing it. So we've got our reference plot database from the Grampians, we have the traits of the species there and their environmental variables. With them, we train our trait SDM. We could make predictions with it internally, but we're also interested in transferring them to new regions on the basis of the environmental variables in the target regions and the traits of the species in those target regions. Okay, don't worry about this side, but then we're going to evaluate those predictions with the area under the ROC curve, the receiver operating curve, and the precision recall curve. So how good are those? So here is our reference region, and this is the area under the receiver operating curve. The grey dots are the individual species and the white dot is the median. So this is saying that the median was just a bit lower than 0.7, which is on the border between fair and poor in a qualitative interpretation. Some are excellent, some are worse than random. These are not fit, this is without fitting the random effects, okay? So they're not trained on the species very strongly. This is the performance in the target regions. And you can see here that the median is about 0.65. Some are worse than random, some are truly excellent, but they seem moderately comparable. Let's draw that comparison a bit further. This figure I've stolen from Christoph Randon's great work, where they evaluated predictive transfer within species in the European Alps when they fitted models in Switzerland and then evaluated them externally in the Austria, or fitted them in Austria and then evaluated them in Switzerland. So this is for tens of species, oaks and pines and firs and other things, but evaluated always within the species. You can see that these distributions of performance are pretty comparable with ours. So that would say that with just 3 traits, we are managing to predict the distributions of these quite well. I bet a bunch of you are saying, but I wouldn't be using area under the ROC curve. Hold that thought. Let's return to our schematic. We would want our models to be predicting presence and absence for the right reason. So here we take our plot data sets that we've got across here that we can evaluate with. Let's say we fitted independent species or taxon-specific regressions to each of the species in each of the regions, took the regression coefficients from those, and then compared them with the trait-based regression predictions, okay? So that we're doing our comparison of the environmental response, thinking of these taxon regressions as gold standards. Here is that comparison. On the x-axis, we have the trait SDM, predicting the coefficients here for the 4 environmental variables. And here we have taxon regressions. The 1-to-1 line, if things were perfect, they would be lying along those 1-to-1 lines. For topographic wetness, at least we have a positive correlation. That the highlighted ones in the front are those in the reference region, those species in the reference region that occur elsewhere. And the ones in the black are only those species that don't occur in the reference region at all. You can see some of these models are not doing very well. Some covariates are fitted well. And we might think that the farther away from the 1-to-1 line, the worse models should perform when evaluated with predicted presences and absences. And so here I'm using the area under the precision recall curve scaled to prevalence. 1 means it's the same as random, positive, bigger numbers mean it's better. So you can see here, this is the miscalibration. So the difference between the regression coefficient that was predicted by a trait SDM versus that from our gold standard. When it's 0, it's a perfect prediction. The farther away, you can see the performance is declining. When the models are perfectly calibrated, sometimes you achieve very good performance. So miscalibrated models perform poorly. Now that is the case for this response variable, this performance variable evaluation. The precision recall curve compares true positives to the true positives and false positives, the predicted positives, against the true positives and the observed positives. It ignores this corner of the confusion matrix, the true negatives. That means that it's not playing the game that the receiver operating curve, which is to, if you predict it, a species doesn't occur anywhere and it's rare, then you've got a good model. Doesn't matter if it predicts the presences. That's why we favor this performance variable. I think I'm probably running out of time, so I won't spend a lot of time on this, other than to show that in each of the regions, the performance does vary. In some regions, it's as good or as good as the Grampians, and it's somewhat correlated with how the regression predictions are predicted. So here in the last graph, here is the area under the precision recall curve for the reference region. Most of them are almost twice as good as random. Here is the distribution across all of our transfers. And the median is about 1.5 times as good as random. Some are truly excellent, some are worse than random. I think that's a lot more honest. Let's then look at each of those individual regions, arrayed here with distance. Firstly, you can see there's a lot of variation within regions. Each of those dots is a single species. The pale dot in the middle is the median for that region. So here is a region 800 kilometers away. Here are two regions very close. The important thing you see is beyond that most of the variation is within regions, is there is no decline with increasing distance away from the reference region. And that's really interesting. So I think we should be doing more of this. This is a really hard problem, severe test out of sampling testing. I think it's relevant to our problem context of where to direct survey effort. The way we think about well-calibrated models leads us to particular performance metrics. And I direct you to this preprint here. With that, thanks very much, and acknowledgement to all of the Indigenous peoples on whose lands some of these data come from.